Okay, so let us begin. So welcome James Greene from Rutgers, who will present on mathematics behind drug resistance in cancer chemotherapy.
All right, well, thank you for having me. So just to be warned, I'm not, I'm an applied mathematician, so I don't do really differential algebra. Maybe I've done some work with identifiability, which I'll talk a little, sort of briefly about. But I'm really an applied mathematician, so all the problems that I really work with are motivated by biology. So I'm not sure what the background is, but I see most of you are mathematicians and not biologists, or don't have much background in biology. So I want to, sort of begin with, maybe I would say like a physicist perspective of the problem, and then talk about the model and some of the beautiful, I think quite nice mathematics that comes out of it. But if you want to ask me questions about, well, anything, but especially biology, if there's something you want to ask about or you don't know, we can obviously have a discussion about that. So please feel free to interrupt me and ask any questions you want. Okay, so yeah, I want to talk about the mathematics behind induced drug resistance in cancer chemotherapy. Really what we're trying to study is not the mechanism by which cells become resistant, but so there's lots of mechanisms by which cells can become resistant, but we're interested more in how do they become resistant, not the exact mechanism, but how does this resistance originate? That's what I'll talk about. So this is just outline, but I'm not sure I'll get to all this, but there's quite a lot here. I might skip over some stuff, but we can talk about a lot of this stuff later. So I assume that at least everybody knows what cancer is. That's really the problem that this is talking about. Cancer is basically just a genetic disease where it's basically a lack of homeostasis, right? Cells should only divide a certain amount. They should essentially think about what's best for the body, the whole, as opposed to what's thinking about what's best for them. So they're like a selfish disease. So cells go wrong and they divide when they shouldn't. That's essentially cancer, but it's much more complicated than that. But that's the way to understand it, at least from a very high level. So we're very good in general at killing cells. Again, most chemotherapies are just poisons. They're sort of maybe advanced poisons, but they're just poisons nonetheless. So we're good at killing lots of cells, but drug resistance is the idea that we can't quite kill every cell, right? And so it's really the fundamental problem in chemotherapy. Why can't we kill pretty much every cell? Some cells stay around, and the disease basically relapses, and then there's nothing you can do. So drug resistance is a very, very complicated phenomenon. I like to show these sort of two pictures just to give an idea. This is sort of just a cartoon of a cell. You can basically see that these are just sort of demonstrating all the things that can go wrong. One of the classic things, one of the most well understood things, is that this is the cell membrane, and there's these sort of pumps called PGP or ABC transporters. They essentially let stuff in and outside of the cell. That's how the cell talks to the environment. You can just imagine that if you upregulate these, you add a lot of these pumps, then the drug comes in, but it goes immediately out. And so the drug can't get to where it's supposed to go, right? The drugs need to typically go to the nucleus and sort of do some sort of damage there. But if they can't get inside or they can't stay inside for very long, then the drugs can't do what they're supposed to do. There's lots of other mechanisms. There's increased metabolism, sort of where the drug is basically eaten before it enters the nucleus. Sequestration, so there's lysosomes that essentially, capture the drug and essentially throw it back out. There's increased repair mechanisms inside the nucleus. You have to get inside the nucleus as well. There's vaults that prevent that. So there's lots of things that can go wrong. There's lots of things that can go bad inside of a cell to make it, drug resistant. It's also even more complicated than that because there's microenvironmental factors. Maybe there's, not enough vascularization, so there's not enough blood supply to actually get the drug to the cells to actually affect them. There's immune responses. There's interactions with the stroma. There's so many things. So the main takeaway from this is just that the drug resistance is very complicated. It's a very, very complicated phenomenon. And there's not going to be any sort of model to understand drug resistance as a whole. That's, of course, not our goal. So what I want to do is sort of write, instead of sort of trying to understand all these different things, a very simplistic model to study the basic properties at a very high level. In fact, I'm not even concerned with the resistance mechanism. I'm not saying mechanisms are bad. A lot of people, when they study these sorts of problems, they consider specific mechanisms like these upregulation of these PGP bumps, for instance. But that's not what I'm concerned with. We're concerned instead with, resistance is basically a black box. Instead, we're concerned with how did the cell become resistant? Where did this resistance originate? There's sort of classical ways that people think about this, but there's lots of new biology that suggests it's much more complicated than we initially thought. So really that's what I'm concerned with. Sort of the punchline is there's basically two ways a cell can become resistant. There's sort of the classical way of thinking about it, this idea of spontaneous resistance versus, so this is sort of drug independent. The cell just became unlucky. There's some sort of random mutation that made it resistant, and therefore it can't be treated with this drug. Or this is idea of drug-induced resistance, so the fact that the drugs are causing a stress response that actually promote resistance. These are fundamentally different. So that's what I want to understand. I also want to understand sort of the general competitive effects between sensitive and resistant cells. So again, these cells are not in isolation. We need to consider the fact that they're competing for the same resources in the same location. So I'm sort of interested in the combination of basically competition and the idea of drug-induced resistance. Maybe just to talk about, again, a little bit more about the biology. The classical mechanism is the spontaneous resistance. Basically, there's some sort of stochastic event. We don't understand why. There's probably something effect with the environment. There's predisposed genetics, but there's some random event. Again, we think of these as like point mutations or gene amplifications. These are sort of just genetic things that made you unlucky. So again, you should maybe think of this picture as you have a tumor. Lots of different, sort of types of cells in there. Most of them are sensitive, but not all of them are. So you apply the drug, you would kill all of the ones that essentially were sensitive. Now the ones that are, were resistant before the drug was applied are free to essentially grow, and then you have a resistant tumor, right? Because these all come from the same place, right? These all come from the resistant phenotype or genotype, I guess. This is again classical. This is how people. Almost every biologist, this is classic Darwinian selection. It's selection and just expansion. I mean, this is how everybody would understand drug resistance. This is what, if you ask, I would say, most biologists, they would say this is how resistance occurs. I mean, this is almost undisputed. Of course, there's the story is actually more complicated, and again, this is generally a recent phenomenon, is that there's sort of now, I claim, it's not just a question of genetics, but it's a question of non-genetic cell state dynamics that basically cause the cells to become resistant. So it's not a question of just genetics, but there's things called epigenetics, where you can sort of have like these modifications on the genome, but not actually altering the genome itself, that essentially allow the cell to be plastic and move between, say, resistant and non-resistant, resistant and sensitive types. So they can essentially switch back and forth. But again, this is still, if we're thinking about it, sort of like random switching. So this is random switching between sensitive and resistant. This is still basically selection, right? It's just becoming resistant by a different mechanism, right? So it's still just Darwinian selection. Again, this is important though, because maybe it's not necessarily rare. Genetic mutations are really thought of as being these rare sort of events that don't occur that often. These are definitely not rare. They happen at a very, very quick time scale, and they're often reversible. So they can switch back and forth. Usually if it's genetic mutations, you don't have two genetic mutations to bring you back to being sensitive. It's like but these can definitely go on and off. So it's very quickly. So that's, again, sort of the same, slightly different perspective, but still sort of selection via Darwinian evolution. That's all it is. The most recent, I would say, is this idea of phenotype plasticity that's induced by the chemotherapeutic agent. So the fact that it's not random switching anymore, but it's switching because the drug is present. So you should think of it like a stress response. You're being attacked by the drug. The cell puts up some sort of response to become more resistant because the drug is present. And that's the idea that I want to understand. This is sort of well known from a couple of different perspectives. How do cancer drugs work? They're basically, they cause genetic mutations. That's essentially what they do. They damage the DNA, and they essentially cause the cell to kill itself. That's basically how all chemotherapies work, right? They just essentially damage the DNA enough so the cell can't divide, and then the cell just dies. So obviously they're attacking the DNA, so we know that they're going to cause mutations, right? It's natural to think that they're going to cause mutations. So of course we expect that they can induce resistance on this level. They're sort of designed to do that. So this is sort of still a genetic question, but I claim it's even more complicated. They can actually induce resistance on the epigenetic, or this sort of phenotype plastic level, via this idea of DNA methylation or histone modifications. So in other words, the drug itself can promote phenotypic state transitions again, due to like chemotherapy or radiation. So these usually occur on a very, very fast time scale. They occur in a dose-dependent way. Obviously, if you apply no drug, then there's no induced resistance, but there's some sort of maybe probably almost certainly nonlinear effect or nonlinear dependence on how much drug you apply and how fast you're essentially promoting resistance evolution. And of course, it's also, since this is on the phenotypic level, so it's often reversible as well. Okay, so that's the biological background. Again, I'm claiming this, and you might say, well, okay, is this actually true? Maybe I'll just run through these rather quickly, but there's lots of experimental evidence, I would say only in the last 10 years. This is one of the famous papers. It's cited many times by Sharma. They have this idea of this sort of dose dependence, induction to a plastic state in a dose-dependent manner. This was 2010. This is one of the papers that really inspired us. This is 2013. Again, they're looking at expression of this MDR1, which is, again, the PGP pumps, the pumps that essentially let stuff inside and outside of the cell. They essentially treated these leukemic cells with a chemotherapeutic agent, and they essentially saw after only a couple days, you have this induction-dominated expression of MDR1. So again, it's not a question of being genetics. It's way too fast to be genetics. It could still be selection. That's a non-trivial question because you could just have fast, sort of fast changes and then selecting very fast, but they actually validated induction on sort of individual cells. So they're essentially watching individual cells change state. So they really are seeing not selection, but they're seeing induction. Again, so this is one of I would say one of the more rigorous examples of how this works. And they have sort of lots of interesting pictures about the phenotype plastic state and sort of dose responses. This is essentially a profile of how resistant the tumor is, or the cells are, the cancer cells are, as a function of the dosage. So you see different states depending on the dosage. So there's clearly a dose dependence on how resistant the population is and how much induction you're getting. There's another paper, maybe I'll talk more about this later. Again, this is sort of similar. This was actually very interesting though as well, a very beautiful paper. The idea was they actually leverage the fact that you're getting induction to actually treat the cells that are induced with an efficient chemotherapy. So you basically have a transition toward a resistant state, and they actually knew how that state was resistant. They were upregulating these SFK molecules, and they essentially were able to then leverage that and treat those with SFK inhibitors and actually get better results than you would expect. So they actually used the fact that the cells were transitioning in a dose-dependent manner to actually design therapies. And so this is very interesting and sort of how you might actually think about sort of using induction to your advantage. This is just some more papers. Again, all these papers are in the last 5 years or so. Most of them are from like 2017 or 2016 or 2015, I guess. Just to show that there really is this plasticity and there's this idea that resistance is not just a random event, but it's actually being affected by how much drug you're treating. Again, you still talk to most biologists. Most biologists will not agree with this. They will still say the cause is primarily just random. You just get random and then you get unlucky and then you get selection. But I claim that this really is a real phenomenon. There's a good amount of papers in sort of a wide variety of different journals that demonstrate that. So I think it's even just to promote this idea of resistance is very interesting because, again, even scientists don't even really know about it. Okay, so again, there's experimental evidence to show that induction plays a role, but the question is, it's still quite difficult to actually determine how this is occurring. Again, sort of disentangling the idea of induction versus just rapid selection is very, very hard. I mean, some people have done it, as I pointed out, that one paper by Pisco, they're actually able to do it, but in vivo, I mean, this might actually even be impossible. So how do you actually go about, sort of differentiating or untangling what's actually going on at a mechanistic level? So experimentally, this is very hard, and I think this is something that math modeling can actually be useful for. It's essentially trivial to understand how this thing, well, I'm not saying what I'm writing is the only thing to write, but it's easy to sort of characterize these things and then study it mathematically and then use that, what can that tell us, what can the math tell us about what's happening mechanistically? And that's how math modeling generally works. So really what we're going to do is sort of discover, how does this origin of resistance affect both quantitative and qualitative dynamics. Maybe even suggest experiments to determine this rate. I claim this rate will be important in terms of therapy outcome. And then, of course, what I really want to talk about is the idea of treatment protocols based on this rate. So in other words, can we design, what are the right control structures to design now that we know this is happening, presumably in vitro? I mean, if it's happening in vitro, if of course it's happening in vitro, then of course it's obviously happening in vivo as well. So presumably this has some sort of clinical outcome. And so how does that affect what our control structure should be? How should doctors treat, right? How should they administer chemotherapy? That's the question that I'm really interested in. Okay, so the model I want to use is very simple. Again, my philosophy is at the beginning to sort of start with the simplest possible thing and sort of study it and tell me what it says, and then from there, obviously, build more complicated things that maybe reflect reality better. But I want to sort of study this phenomenon, I claim, in the basic, the bare bones of it. So what are we going to do? We basically assume that we have two populations of cells. Let's say we have sensitive and resistant cells. And so basically what's happening is that, okay, so we have sensitive and resistant cells by SNR. We have a treatment which we're assuming is represented by U of T. Again, I'm not modeling sort of any kind of pharmacokinetics. I'm just assuming that I can control precisely how much drug the tumor sees at any instant. Again, that's not realistic, of course, but again, I want to consider the basic simplest possible thing. And so the idea is that the treatment does two things. So presumably it's affecting, right? It's affecting the sensitive cells and the resistant cells as well. So it's killing cells, but it's also promoting resistance. So that's the key term I'm really interested in here is this sort of alpha U of T. So the application of the drug induces transitions now from the sensitive compartment to the resistant compartment. We assume, of course, that we have sort of random mutations that are either phenotypic or genetic as well. But the interesting thing that I'm sort of concerned about is this idea of, when you treatment now does two different things. It, of course, makes the tumor smaller, but also promotes a phenotype that you can treat less effectively. So now it's less obvious what to do, right? It's less obvious what sort of chemotherapy to apply because, again, it has this sort of contradictory effects.
What's the last term? It's also some transition, right?
Yeah. So
in that direction.
Yeah. So we'll assume that again, I assume if it's plastic, the phenotype is not stable, right? It might transition back. Again, if it's genetic, I probably shouldn't have this, or maybe the value should be very small. But again, if you become resistant, you can also go back to being sensitive. So that's again what phenotype plasticity is.
Right. But you sort of assume that the proportion of induced cells is constant inside resistant, right? If you write this.
Wait. So could you say it again? So what do you mean?
So what you write here, right, is that at each point, at each time point, the same proportion of resistant cells might become non-resistant.
Yeah, there's a constant per capita. Fix a dose, right? Fix a dose. You're saying fix a dose, yes.
Yeah, but now does that mean that you assume that sort of induced resistant cells constitute a constant proportion of all resistant cells? Because non-induced, they cannot go back, right? Or they do it rarely.
Right. So it's a good question. So yeah, what I'm basically doing is I'm lumping all of the cells into one compartment, right? So yes, I agree. We've also thought about that, but I'm not going to write it here. But we also thought about, are all those resistant cells the same, right? So what you're saying is there's some that are maybe induced.
Basically my question.
Right. No, I agree, and it'll probably be more realistic, of course. Then of course we have more parameters, and I don't like having 1,000 parameters. But yes, I agree 100%. That is probably a more realistic thing as well. That induced resistant cells look different than resistant cells. But right now I'm just assuming that maybe experimentally we can't distinguish all of these resistant cells, so I just lump them all together for now. But that could be possible, I agree. Yeah. And that would be maybe realistic, yeah.
Sorry, you're talking about the last term and the second?
Well, I think he was talking about...
Last term in both.
Yeah, in this one, right? Yeah.
Oh, but
the back...
the same term, but one's plus, one's minus, because...
Yes.
Okay.
But he was saying, I think, that the idea that you have... sort of these are the transitions from all of the resistant cells, not just the induced ones, right? Yes. That was what he was trying to get at, right? Because we have I'm sort of lumping all of the resistant cells into one category, right? Which probably is not realistic, but as a first go, it might be okay. I don't know, I have no idea. I'm not saying it's reality, but I'm saying I'm just trying to understand what the dynamics of this look like, right? Or no, do you have an objection to that?
No question.
Oh, okay, yeah, I got it.
Okay.
Yeah.
So the D and the D sub R and R sub R just proportional constants.
Yeah.
And what is K? Capital K.
It's a carrying capacity. So that's another thing. We're assuming that there's some sort of competition. So V is just the total number of cells, the total size of the tumor. So the idea is, again, that there's some competition, right? They're competing for the same resources. They're in the same space. So we're interested not just in the induced resistance, but how sensitive cells and resistant cells are competing with one another. I mean, again, that's also a fairly new concept, the idea of, people call it metronomic therapy, the idea that you can leverage the fact that you have sensitive cells that are inhibiting the amount of resistant cells that are growing, right? So, right, that's an interesting question, right? Of, if you kill too many cells, then S gets low, and therefore this term gets close to zero. So then you can just have resistance that can grow, right? But maybe keeping around the sensitive cells to keep the resistant cells in check is an interesting question, right? And that's the idea of leveraging competition, right? That's sort of what people want. I mean, that's a very new concept, but there's a lot of experimental evidence suggests, even clinical, that not killing everything is actually beneficial and the idea is because there's competition between the two.
And so which of the parameters are known?
Well, that's a very good question. No, I would say, okay, so we have guesses for carrying capacities. We can probably measure these. It depends on the situation again. I mean, it depends on what type of thing I'm modeling, right? It depends on what the resistance mechanism, where is it again, what type of person is it in. I mean, there's it'll vary by person to person or cancer to cancer. But I mean, I would say everything is probably known except for alpha. I think alpha is completely unknown. I don't think there's any good measurements. I mean, that's something that we're trying to work on now. We were working with some of those papers that I mentioned before. But again, even writing it like this is maybe not even right? Because this just says it's proportional to how much drug you're putting in. But that might not even be right? The functional form, it might not be proportional to how much you put in. Maybe there's a sort of a logistic or a sigmoidal dependence. I mean, this is just the most basic thing that you can write. So I agree, this is completely unknown, but I claim it's the simplest thing you can possibly write. But I agree, that's 100% unknown. There's you can do back of the envelope calculations on how many mutations occur on average on a per base pair or something like that. But they're generally very small. But everything else, I would say there is at least some idea of the parameters.
What are D and D sub R?
It's just the induced death rates, right? You kill sensitive cells presumably at a different rate than you kill resistant cells, right? So this is a log kill. Again, it's one of the classical ways. You basically, given a dose, you kill a given fraction of the cells. That's exactly what that means. Again, not the only way to write. I'm not saying that's always right either, but again, it's basically the simplest thing you can write. But just, the effectiveness of the chemotherapy. So D and DR represent how effective it is on sensitive and resistant cells, respectively.
So why isn't there, say the first equation, why isn't there a term proportional to UT and R?
What do you mean? Wait, UT and R? What would that term represent?
Equation.
Yeah, why would this?
Well, it would represent that.
Because you're saying that why?
Yeah.
But this is a stress response, right? So presumably, if their drug is being applied, the cell doesn't become more sensitive to the drug as the response occurs, right? The idea of this is a stress response. So U is like a stress on the cell. So the more stress that is applied, the more defense mechanisms go up. That means transitioning into R. That's what defense is in this case, right? That's how you're defining defense. Wouldn't really make. I don't think there's any good experimental evidence. I'm not saying it's not possible, but I don't think there's any experimental evidence to suggest that you apply more drug and the cells should become more sensitive. I don't know if I see that. I don't know if I've ever seen that. I don't know why that would occur. All right, other questions?
So when you say a resistant cell, that's not completely resistant.
No, well, I'll talk about that in a second, but yeah, it's a defection of DR, right? If DR is 0, yes, right, it is, right? If a DR is 0. But I'll do that in a second, actually, to make it simpler. And of course, but of course I'm calling this resistant, so I should at least assume that DR is less than D, otherwise it doesn't make sense, right? Because the drug is less effective against R than S.
So why?
Oh, sorry.
Why wouldn't the minus gamma R absorb the first term in the second equation?
The first term in the first term here in this.
No, the R sub R times 1 minus the carrying capacity ratio
Yeah.
times R. Well, Oh, V is varying.
Yeah, V is not constant, right? V is S plus R. Just write it like this to maybe V is the total tumor size, so it's not a constant, definitely. Otherwise, just exponential growth, and there's no competition. But I'm interested in the competition as well. Okay, so to make things simpler, again, the thing that I'm really interested in, the thing that we were really interested in, is the idea of this induction and the essentially the competition. So I'm going to make essentially no back mutations for now. Again, you can show under some small values, again, use a continuity argument to suggest that the results won't change, and we've done that. But for now, I'm just going to let no back mutations, so when you become resistant, you stay resistant forever. And I'm going to do complete resistance. So I can't do anything with the resistant cells. I can't touch them. They're completely resistant. Is this good or bad? Well, I mean, yeah, of course it makes our life simpler, and especially, well, okay, so let me go to the next slide for a second. Yeah.
But what did happen with capital K?
I just non-dimensionalized it.
No.
So I just, because K is a constant, right? It's just a carrying factor. So I just non-dimensionalized to 1, and I just removed the term here and made this PR.
Okay.
So PR is just between 0 and 1. It's note I should always assume that PR is less than 1 to make the resistant cells actually grow slower than the sensitive cells. Otherwise, there's almost no logical strategy to do, because you'd be promoting resistance to a faster growing phenotype. Almost any sort of strategy you would do would be any logical strategy would be not to treat, right, basically. Well, okay, anyway, and there's also experimental evidence that suggests this, because resistant cells typically have to give up something to become resistant, right? They have to essentially, it's a zero-sum game. You have to make yourself less sensitive to the drug, you essentially have to grow slower. You have to add some other machinery. So it's not a restrictive assumption. This is widely seen in experiments. Okay, so the question is, okay, asymptotically, is this interesting? Well, I would say no. I mean, basically it's clear, because there's essentially, no matter what treatment you're applying, there's a leakage term in this epsilon that no matter what happens, and there's a carrying capacity, everything always becomes completely resistant. So resistance always wins no matter what sort of control you apply. Any bounded, measurable control you apply, you're always going to get a tumor that approaches fully resistant. Now, is that realistic? Well, I would say maybe it's not that unrealistic. I mean, cancer is a disease that, it's a disease of old age, essentially. I mean, in some sense, it's not unreasonable to think that everybody will get cancer eventually, right? Because it's a disease of mutations. The longer you live, the more mutations you have, the less stable your genome becomes. So it's not really that unrealistic, right? It's not really that an unrealistic of assumption. Of course, this is only one treatment. If you look at what clinicians do, they never use one treatment. It's always many combinations of therapy. So it's not also unreasonable to think that one treatment will always fail in the long run. So I would say it's not necessarily a bad assumption in terms of reality. But of course, mathematically, at least asymptotically, it's not interesting. No matter what you do, you're always going to lose, right? In that sense. Okay. So even though asymptotically all trajectories approach this, of course we're not necessarily interested in asymptotic dynamics, right? Because again, if we can prolong the patient so the cancer won't kill them until 200 years old, then it doesn't matter, right? Because they'll die from something else before that, right? That's not necessarily, asymptotics aren't everything. So really the question that we're interested in is, can we use, what can we do transiently? Maybe the transient dynamics might be very different for different controls. Even though the controls all lead to the same asymptotic dynamics, the transient dynamics could be very, very different. So that's the question that we're interested in. And the idea is, because you have these two you have this competition between the resistant and sensitive cells, that maybe you can utilize this competition to prolong patient life, and such that it can be long enough so that you can either at least maximize the efficiency of a treatment, right? So there's still some essence of control. And again, I use control in quotes here. I mean, it depends what you mean by that. But you can still at least you can do something. It's not like everything is out of your hands. And this is sort of interesting again, because therapy has contradictory effects. So the question then becomes because if we're going to eventually talk about optimization, we have to talk about what is our metric. It would seem very artificial to just say, well, we fix a finite time horizon and we say we want to minimize the tumor size at some final time. I mean, that seems artificial, right? Because eventually the tumor is going to win anyway, right? I mean, we already know that's already built into the model, essentially. So the way that we rank therapies is that we essentially pick some tumor volume that we consider dangerous. So we call that VC. VC will be like the clinically unacceptable tumor size. And we essentially want to maximize the time until you get above VC. So this is our sort of toy clinical experiment. We assume that the cancer is initiated at time 0. We don't model that at all. I have no idea. We're not considering that in this model, but it's initiated by some small number of cells. Detection occurs at some critical tumor volume, at like, let's say, some screening. Treatment occurs. We apply some sort of control, some sort of therapy here, up until the tumor reaches size VC, which we know will happen as long as VC is less than 1. And this time is how we measure how effective the therapy is. And so a good therapy is a therapy that makes TC longer, right? So that's our metric here. Again, I would say this is a toy clinical problem, but it is sort of a clinical problem. This is similar to what is done. I'm not going to claim it's exactly what's done, but this is essentially, they'll keep using this therapy until the tumor gets too big, and then they'll decide to move to another therapy. Now, again, they're not exactly doing that. They're also looking at rates. They're also looking at how fast they're growing in between biopsies and things like that. But again, I want to sort of do the simplest possible thing that's inspired by something clinical. Okay, so that's our metric. Okay, so the first question is, maybe I'll skip through this because I want to talk about some of the math stuff. Does it matter? The idea is, like, do we actually care about this? Basically, we take two different, two standard therapy protocols. We take constant therapy and pulse therapy. So you think of this as like a constant infusion. This is where you're maybe taking a pill every day or something like that. Does it actually affect the treatment outcome? In other words, is this best for one of the values of alpha, and is this best for the other values of alpha, at least for some patients? So is knowing how much the treatment induces resistance, is that important? Does that actually decide which of these two therapies you should do? Should you do one of them in this case and another in this case? That's one of the ways you can sort of decide if it actually matters. The answer, as you might guess, is yes. You can take alpha 0, so the non-induced case. For this example of parameters, the constant therapy is better, or if you take everything exactly the same, the pulse therapy is better. In the case when you have, let's say, alpha, again, this is sort of a back-of-the-envelope calculation as like 10 to the minus 2. So it does actually matter from the patient's perspective. It matters, what the value of alpha is. That should dictate, at least on some level, what therapy you should use. So again, maybe that was obvious, but that's at least something that needs to be at least said at some point to decide which therapy is better. Note that it's also not just the fact that you're applying more drug here and more drug here. You're actually applying less drug with the pulse therapy, but you're doing better. So it's not just a question of the amount of drug that you're applying either. But okay, so you can believe me on that. Okay, so that is...
It actually looked like you, with the pulsatile therapy with the alpha to equal 10 to the minus 2,
yeah.
You actually do hit the red line well before.
You have to go above the red line. I mean, you have to go above it. That's the question. I mean, I agree. There is some sort of, there is some sort of like, you might say, well, okay, you're basically crossing the red line here. And I agree, but we have to sort of decide what a clinician would have said. Yeah, exactly right. We have to sort of decide what our metric is. We have to, and for this to even make sense, of course, this has to be a closed set, so it has to go outside of the closed set. Well, we'll talk about that in a second. But I agree. I mean, you could look at this and you can say, well, maybe you're sort of just playing a game with me. And in some sense, there is something to be said for that. But, the question is still, you could still do better with this therapy, right? That, at least by our measure. At least by our measure.
What you're saying, it has to hit the red line and stay above it.
It has to at least go, no, it just has to go above it at some point.
Go above it.
Mm-hmm. It has to leave a close set. I mean, I'll have a better picture of this in a second. Okay, so there's the question. So at least we know it matters. So from a patient's perspective then, the idea is then, we imagine our clinical scenario is then, what we'd ideally like to do is, sort of take a biopsy from a patient, measure their value of alpha, and then decide the therapy based on that. This is not like an unreasonable thing. This is sort of what people try and do now. We basically, we want to first determine the value of alpha and then design a therapy based on that value of alpha. As we saw from this, the value of alpha might severely, it might drastically affect what therapy we should apply. So a fundamental goal is, can we evaluate, can we actually find out what the value of alpha, what is this induction parameter from some sort of finite measurements? So that, of course, is natural to identifiability. So we have to basically ask the question, is alpha an identifiable parameter? From this, just to be clear, we're only going to assume that you can measure the total tumor volume, so I can't measure the sensitive and resistant population individually. That's why it's essentially a little bit non-trivial. Because, generally you can't assume that from a general, you go to a hospital, they can't usually, they don't do like deep sequencing, so you don't exactly see the genetic makeup of, you don't see the genetic makeup of the cells individually, you just see the size of the tumor, basically. Okay, so then we can do probably stuff that you're very familiar with. Again, this is not exactly my field, but I've done some of it. This is a standard, writing the system in more standard, sort of control input-output way. We have basically a control-affine system. Our output is, again, the total tumor size. The idea is then that we can essentially measure the outputs, so we can measure Y perfectly and all of its derivatives for different therapies. And the idea is, can we determine can we design therapies to essentially determine all of the parameters from these measurements? This is fundamentally related to the Lie derivatives and the iterated Lie derivatives. Maybe I could have a better slide on this later. Okay, this talks about unique structural identifiability. Essentially, we want to know, is this map injective, the map that sends parameters to essentially the output? Is this an identifiable? Is this map injective? Is there only one? Is this one-to-one? Again, there's the sort of two standard sets of observables that we have. We have these, which are just essentially the measurements of the output function, all the derivatives at time t equals 0. This is sort of the natural measurement function. This is the natural set of observables. And the fundamental question is, well, this is related to the other set of observables that are essentially just the iterated Lie derivatives of the output function. And there's basically a theorem that says that as long as your set is basically nice, then these two things are the same. So these are real observables. The iterated Lie derivatives are the sort of other observables, but you can essentially always write the iterated Lie derivatives. You can write these in terms of the iterated Lie derivatives. So those two sets of observables are the same, basically, right? So instead of the question of asking, is this map from the parameters to the output identifiable, it just becomes essentially the map to the iterated Lie derivatives. Is that injective, right? That's essentially what the question becomes. So it's just enough to just look at the iterated Lie derivatives of the vector field to actually answer the question of structural identifiability. And so you can do a standard analysis of this. And you can show that you can get every single set of parameters from a relatively small set of iterated Lie derivatives, because this is a small, it's a very small system of differential equations. And so we can actually determine, using some sort of computer algebra, or I don't remember how I did this even, but you can determine the parameters from these measurements, from the iterated Lie derivatives, which are the observables. Again, we did it another way where you actually do it directly from applying different measurements, applying different controls, and measuring the y's, so the higher order derivatives, and you can actually show that you can get it with only four different control functions. So the question is just, yes, it is identifiable. That's the main thing I want to say with this. So yeah, so it is identifiable, at least structurally. Of course, again, this is a little unrealistic. Because again, if you're actually doing this experimentally, you just actually have to measure the volume and its derivative and its higher order derivatives at time t equals 0. Again, you have to essentially end up evaluating third order derivatives on data, that's very, very dicey. Even evaluating one derivative on data is probably really dicey. So we ask questions about practical identifiability, but maybe I'll just skip this. There's some interesting things that happen in terms of the dose response curves, but I really want to get to something else. But there are some questions about practical identifiability that are still open. But it is practically identifiable in maybe a slightly different sense. But okay, so maybe I'll just skip that for now. Because I really want to talk about the control problem in the last, how long do I have? Is it still 3 or is it till, I just don't know.
Oh, okay.
Or no, is it?
20 minutes, we started 3 minutes later.
Okay. That's fine. Okay, but so now we imagine, now we have the situation where we basically assume now that we have, we can identify this rate. So we know two things. We know the treatment is affected by this rate. What sort of treatments should you apply? And we know that we can at least identify this rate. So again, the situation that we have in mind is sort of measuring this rate and designing therapies after we identify this rate. So that's, so it's natural then to ask, what is the best therapy? So this is a natural then optimal control problem. And so, the thing that we're really interested in is how does this optimal control depend on this rate? How does the optimal control structure? How does the qualitative features of this optimal control change as we vary this induction rate? Is there something we can say about that? Again, that's obviously very clinically relevant because, again, that's what we want to do. If you're imagining this as a clinical scenario, we're trying to design therapies for patients, and so we want to know how to apply therapies given we know that there are set of parameter values. It also gives another, sort of testable, maybe in vitro way of determining alpha, because if we know that how the optimal therapies change, and we, do a bunch of different therapies, we measure which one's optimal, then we can reverse engineer what the value of alpha is as well. So it's clearly something that, it makes sense to be interested in. Okay, so what is the optimal control problem? Again, this is the same picture I had before. We imagine a clinical scenario where we start detection at a certain size VD, and then we want to treat up until the tumor reaches some critical size VC. So maybe visualizing this in the phase space, which is a little bit easier to see, basically what we want to do is we want to keep the trajectory inside this box, or this triangle, for as long as possible. So now it's
what are coordinates?
It's just S and R, right? So sensitive and resistant population. So it's just the phase plane, phase plane, right? So I just want to keep the trajectory. I assume I start the trajectory somewhere down here. I detect it this time, but I want to keep the trajectory inside this red box for as long as possible. So I have a maximum time optimal control problem. That's exactly what this corresponds to. So that's just stating this precisely. Of course, the set that we want to maximize over is, we have some sort of bound on the functions, on the controls. We assume that there's some sort of toxicity constraints, so we can't apply infinite amount of drug, or we don't even have the resources to do that. And of course, but the set that we need to do to talk about existence and things like that is Lebesgue measurables. So that's the set. We want to essentially maximize the time that I remain inside this region, and I want to try and see if that even exists. Note that this is not an unconstrained problem, so there's a technical difficulty here that we have to sort of address. But this is, this is a closed set, right? So, there's a path constraint that's enforced along this entire system, that the fact that I can't go outside of this line. So it's not just it's not like an open set condition exactly, but we're trying to, we have a closed set condition that has this extra path constraint that we need to be concerned about. Okay, so maybe I should, skip. Okay, so the first question is, we want to use the maximum principle to understand this optimal control, but we first have to say that this actually exists, right? It's a non-trivial thing to actually show that this exists. Note that you might say, well, it's a maximum time problem. This is sort of well studied because the minimum time problem is well studied. And it's just a matter of taking -1, right? Maximum time, minimum time are just related by a -1, but it's actually not so trivial. Because minimum time problems will basically always have an existence. The inf will always be finite. The question for this problem is the soup finite? If the soup is not finite of all these the critical times over the entire control set, then the optimal control won't exist, and the maximum condition, the maximum principle will be vacuous. So we need to actually establish that this soup of trajectories that essentially stay inside this box, the time of staying inside this box, is actually well defined. Is actually finite. Again, in this case, it's actually okay, because again, we know that 0, 1 is globally attracting, and so you can use some sort of, you say essentially weak solutions to this, and you can actually construct a solution otherwise that wouldn't, so it's actually okay. But just to be clear, there's something that needs to be said for that. It's not immediately obvious. It's not exactly, the minimum time problem is almost always simpler in this case, and you never have to worry about, but the maximum time problem is actually much trickier. In fact, I've never seen anybody do a maximum time problem before. I couldn't find any literature on this. It's not a standard problem. Minimum time problems are standard from engineering. Minimum time to land, to bring a car to a stop or something like that. These are very natural questions. But maximum time is a little bit, it's a little unusual in that sense. But so definitely it does exist. Again, there's technically an argument here, and you have to use some convergence in the. Well, you can use a couple different ways of doing it, but weak convergence essentially. But you can actually, otherwise, you could construct a control that would stay inside of that set. It would stay away from 0, 1 for all time, but that's a contradiction. So you can do it, but it takes a little bit of finesse. So that allows us to really say that the maximum does exist. So the soup is really a max, and so we can use the maximum principle to actually study the optimal control. Again, there is a slight technicality that I need because the maximum principle is fundamentally an open set condition, just like the first derivative test or something. But I don't have an open set here, right? I have a closed set, and the issue is that this line, the line that defines VC, is definitely obtainable. So that definitely occurs, and you can stay along that for a certain amount of time. So the maximum principle needs to essentially be broken into two parts. It needs to be broken into a part where the trajectories that are interior to this set and the ones that lie across this line. And so you can prove, again, it takes a little bit of, well, you can prove it, it's relatively straightforward. I mean, it's essentially the principle of optimality, or Bell's condition, that essentially the controls that maximize this are essentially satisfying unconstrained maximum principle interior to the set, and on the exterior, on the boundary, the control is uniquely determined by this. So there's one trajectory, there's one control that keeps you along that trajectory, along the line v equals vc. So essentially, you can break the problem into two parts. The part that are interior, that satisfies a regular maximum principle, it's the standard Pontryagin maximum principle, and the controls that are along this the boundary, which are given precisely by a definite formula. So essentially the theorem says that you can essentially concatenate the two. So it's a question of just putting them together. The interior controls satisfy a regular maximum principle, and the ones on the boundary are given precisely by this, where S plus R is equal to VC. So then it's enough to just look at the interior. I mean, now that we know exactly what happens on the boundary, we just need to look at what happens on the interior.
But so, may I ask?
Yeah.
But now you can play sort of trade-off game, right? So you can stay longer in the interior but less on the boundary, or less in the interior and longer on the boundary.
Right.
So you like. So then I'm not sure. I'm interested what do you mean by concatenating to
Well, I'm saying that the solution itself will be a concatenation of what happens on the interior and what happens on the boundary, and the necessary and you know what happens on the boundary, so it's exactly this. Now the question is, I just need to know what happens on the boundary. I just need to know what happens in the interior, right?
Yeah, but the point where you get on the boundary,
yeah,
it depends on what happens in the interior, right? Where the optimal pathway interior ends.
Right. So I just need to understand the conditions, what the solution looks like at the interior, right? But it doesn't matter. Any point in the interior will have a similar necessary. It will have the exact same necessary conditions, right? So I agree.
Exactly the same.
Yes. Well, we'll see. Yeah, exactly. Yeah. So exactly the same necessary conditions. So the structure, the qualitative structure, won't change.
Okay.
Okay. Well, let me see. So we'll see that. Okay, so now we know a solution exists, and we know how to essentially make it a completely interior problem. So we essentially remove the path constraint. Now we just have a maximum principle between 2 points in the interior. So then we can just, to understand what happens in the interior, we can just use the standard maximum principle, where we essentially minimize. Note I'm changing this to a minimization problem just to be consistent with the literature. Again, everybody uses minimization, so I made this -1. So now I want to minimize this Hamiltonian point-wise with respect to the control, right? So that's the use of this. You lift to the cotangent bundle, but I made it a harder problem. But the minimization to this is actually much easier because it's a point-wise condition on the control U. So now the question just becomes interior to the set, just minimizing this function point-wise. And again, since it's affine in U, that's very easy. It just depends on the switching function. There's some facts here that are not so important. The abnormal extremal exists. Abnormal extremals are easy to classify, so we can forget about that. So again, Hamiltonian is identically 0 because there's no explicit time in it. And so the switching function just takes the very special form where it's essentially the adjoint, interior product, the inner product of the adjoint with G, which G is the coefficient of U in the control problem. And so then, since this is linear, we know exactly, depending on the sign of phi, what exactly the control looks like in the interior. So if phi is positive, the control is 0, so we're at the minimum dose. If the phi is negative, then we're at the maximum dose. Of course, when phi is 0, we don't know yet. We have to do more work, but basically everywhere interior to the control structure, everywhere interior, we know precisely the control structure away from where phi is equal to 0. So again, this is sort of standard, so maybe I don't need to go into it too much. So we basically know the control structure is bang bang, outside of course, possible singular arcs. So that's really the question we want to address. As long as phi is not 0 or phi is not identically 0, we know the structure is just bang bang. So between m and 0, where the switching points are given by the zeros of phi. But the question is can phi be identically 0 on any interval? If it's identically 0 on any interval, then maybe we have intermediate doses that we should apply. So that's the question that we're interested in understanding. What subsets are these singular arcs allowed? Can I apply intermediate doses, or are intermediate doses optimal In particular, how does the geometry of these singular arcs, how does this structure depend on alpha? Again, that's really my fundamental question, is how does alpha change this geometry? And of course, the question is, the original question is, are these optimal? So these are differential geometric arguments. Again, planar systems that essentially Sussman did. Maybe this is a slight generalization, but very, very similar to what he did. Let's look at this. Okay, but again, the switching function on a singular arc must be identically 0. That's a strong condition because it implies that all the derivatives are 0. So we can essentially, and furthermore, these derivatives can be calculated in terms of the Lie brackets. So the Lie brackets essentially determine the switching function and all of its derivatives precisely. Because the system is control-affine. If it's not control-affine, then this will completely fail. But we can essentially understand what's happening to the switching function by looking at the Lie brackets, or the iterated Lie brackets, or the adjoint endomorphism, if that's how you want. That's really the right way of saying it, I guess, of the vector fields f and g. Now, the key observation that is actually quite useful here is that the vector fields f and g are linearly independent, and again, it's easy to check. And so the Lie bracket, which itself is a vector field, can be written as a linear combination of f and g. Because they're independent, this is just an arbitrary vector field. And in fact, we can find it explicitly. I claim that the singular arc is fundamentally tied to the f coefficient of this Lie bracket. Why is this? Well, essentially because the derivative is in terms of the Lie bracket is in terms of f and g. It essentially allows me to write the first derivative of the switching function just in terms of these coefficients. So this is just an ODE for the switching function, and since the switching function has to be identically 0, wherever a singular arc occurs, well, okay, this is obviously 0, so the only way this is identically 0 is if gamma is identically 0. So where gamma is 0 is the only place where singular arcs can occur. Again, this is a purely geometric condition on the phase space. It has nothing to do with time. It just tells you exactly in the phase plane, in the SR plane, where switchings can occur, where singular arcs can occur.
Where does x of t comes from?
X of t is just SR. I'm just writing it as, I don't want to write a vector, but it's just the vector SR.
It's just like, okay. Mm-hmm.
Yeah, this is just an ODE, right? This is just a system of ODEs, right? So now you have a system of ODEs, you have an equation for x dot, you have an equation for phi dot, and so you've closed the system. The idea is this allows you to write just a completely closed system for x and phi. You can forget about the adjoint. The adjoint is given is away. We don't care. The adjoint is gone. I've eliminated the adjoint because of this independence. So it alleviates that annoying calculation, essentially, or it alleviates the adjoint. Now, this is why you can do this in 2 dimensions, but in 3 dimensions, the problem is completely open because there's no nice characterization in 3 dimensions or not. This won't be true in general because these won't be a spanning set of the vector field, so you won't be able to characterize the Lie bracket in that case. So that's why 2 dimensions is in some sense easy, easier, but 3 dimensions are higher or hard. Okay, so this tells us, this is a theorem then, that singular arcs can only occur where gamma is equal to 0. So, and I can compute gamma explicitly. In fact, gamma is some constant, well, some function, but some positive function times essentially a line. So the singular arcs can only occur on a line in the SR plane, and I know exactly where that line is. So maybe just as a picture, maybe denoting sort of the 2 extremal vector fields, so no treatment and full treatment by x and y respectively. The structure then of the control at the interior is as following. So you know that you have only yx arcs. So when I say yx, I mean a y arc followed by an x arc. So this is full treatment followed by no treatment here. This is no treatment followed by full treatment here, with at most 1 switch in each of those regions, because the switching function can't be identically 0 in there, so it can only have 1, 0. So there can only be 1 switch. And the singular arcs lie on here. So the intermediate doses are only applicable in this curve, this line here. And under certain easy constraints, this line definitely is in the SR plane. So this line really exists like I've drawn it. It's not somewhere over here, somewhere negative. It really exists like that. So now essentially we have a good strong result. Well, we're almost there. We're getting there. We know what the control structure looks locally in here. We know what the control structure looks locally in here. The control structure on here, well, we can determine that as well. It's uniquely determined because you're staying on a fixed line. You can just solve for essentially the Lie derivatives, where the Lie derivative is 0. the lead derivative of the vector field is 0 along here, so there's one unique control that keeps you on there, and that this really is obtainable and actually extremal. So this really is a feasible. It does satisfy the necessary conditions. So this is really a control that you could apply that is actually extremal. At least, you know, there's a subset of it. That's what this purple is. So there's a subset of this full line where the control really, the singular control is really between 0 and m. The idea is that, of course, as you move up along this line, the control hits m, and then you have to essentially move off of it.
So, but gamma is an affine function, right? So lead derivative of gamma will be.
No, it's not affine. No, it's not. There's a constant multiply. It's not affine. There was a determinant that I had to get rid of. It's not easy to compute that lead derivative. Let me.
Okay.
Because there's a term that didn't affect the sign. There's a constant that didn't affect the sign. So it's like L gamma times the determinant of f and g, which I always know is positive or something like that. So it's more complicated than just. It's not just as plus br minus c.
Okay.
It didn't affect the sign, and therefore it didn't affect the zeros. That's why I don't care about it. When I view it like this, but taking the lead derivative will be a little bit more complicated. I mean, you could do it; it's a standard computation, but it's a bit of a pain. Okay, so now the question is, so now I really want to answer the question. I think I can do it in the last couple of minutes. How does the control structure change? So now really what I'm asking is, how does this line change as alpha changes? How does the singular arc change as alpha changes? Well, in the case when alpha is equal to 0, that line is actually horizontal. You can check that b, or one of the constants, was 0, so it's just a horizontal line. But we know that trajectories are always moving in this direction because r is always increasing, so therefore you can never stay on this arc. So there's no singular arcs, and in fact, you know, interior to this, the control structure is just a concatenation of essentially one bang, maybe a control that leaves you on here, maybe another y arc, but that's it. Okay, so there's some technical details here that I'm slipping over, but you can precisely characterize the control structure as an on arc and off arc, an arc that stays possibly on this for some amount of time, and possibly one other y arc. So the control structure is completely determined. And again, that's just because of the geometry of this arc. The arc is horizontal and you can't stay on it. And you can't even switch across it, right? That's the idea. You can't switch across it either. Okay, so now the question becomes, what happens as we increase alpha? How does this arc change? Is the arc optimal? Is singular arcs optimal? And how does the switching structure change? So now you can show that this line actually, has a slope, and so I can actually stay on it now, possibly. And so singular arcs could be optimal, or I could switch around it. Well, it would have been interesting if singular arcs were optimal. In other words, intermediate doses were optimal, but the case is actually that's not the case. You can actually show using a variety of techniques. There's the Legendre-Clepsch condition, which is essentially just a second order, a higher order condition. It's violated, so the arc is definitely fast for us. Another maybe more geometric way of thinking about this is there's actually a clock form, and you can use Stokes' theorem to essentially evaluate. You can compare trajectories that do x, y, or that stay along the singular arc, and you can always show that staying along the singular arc is actually faster, so therefore it's worse for us. So singular arcs are definitely not optimal, not even when alpha is positive. So in that sense, the control structure is very similar. So we still know the control structure is bang, bang, but the question is, how many bangs are there in the case as alpha increases? We know when n is equal to, when alpha is equal to 0, there's only one bang. But now, as alpha gets bigger, this line becomes essentially more feasible. So this is alpha is equal to 0. The line is horizontal. I can't switch around it at all. When alpha is maybe small, the line becomes sort of small. Maybe I could have 1 or 2 switches. But as alpha becomes bigger and bigger, this line becomes more and more feasible, and I can have more and more switches. So the bang-bang structure fundamentally changes as alpha increases. So that's sort of a hypothesis. We're still numerically testing this. I don't know how any other theoretical way of doing it at this point. But essentially what we're asking is, how does the control structure change? So it looks like the bang-bang structure changes as you increase the induction rate. Again, up to a certain point. So we might imagine a situation like this, where if this is the induction rate and this is the number of switches, we essentially know when the number of switches is 1, or when alpha is small, we know the number of switches is 1. You imagine that the number of switches increases up until some point where the line will essentially become vertical, and you can't have any switches across a vertical line. But so we expect there to be some interesting sort of non-monotonic behavior what the optimal trajectory should, or the optimal strategy should look like as you increase and change alpha. Again, this is just a cartoon at the moment, but we have people working on that. And so that's the, and again, I should argue that there's also some interesting, you can also use, you could have asked before that, maybe there is infinitely many switches in a region, but you need the singular arc order 2 in that case, so there's variational vector field arguments that you can make that show that actually in each neighborhood there's at most one switch because the arc is of order 1. So actually it really is just bang bang, and the controls aren't actually measurable. You don't need measurable in this case, you just need piecewise continuous, because you only have a finite number of switches. But so that's the question I'm really interested in. How does this change? And at least we see from the geometry of this that the number of switches, the number of times you should turn treatment on and off, increases as you increase alpha, at least up to a certain point. And so this is actually extremely clinically relevant because it suggests different treatment strategies based on how mutagenic the chemotherapy is. And also provides a testable hypothesis to determine alpha in vitro as well. And so that's really the summary of this work, and so, this part of this work. But so, there's some other stuff I can talk about as well. There's future work that we're working on, more interesting things, more interesting systems, and sort of the idea of combination therapies that I was talking about before. Essentially applying, sort of leveraging the fact that you're having induced resistance to actually, decide versus combination versus sequential therapy. And so we're starting to think about that, and the control structure there is also extremely interesting. Obviously harder because it's a higher dimensional and there's more controls, but also extremely interesting as well. So I guess that's it. I'll go for that. Any questions? And thank you.
Thank you. But this function n of alpha, but does it already also depend on the starting point?
Yeah, it depends on the initial conditions, definitely.
So it's n of alpha and of initial conditions.
Right, of course, and it depends on every other parameter as well. But the interesting thing, I'm imagining I'm fixing all those other parameters. I just want to, I'm fixing the initial conditions. I'm trying to compare apples to apples. Like I'm trying to just compare everything else the same. Just how does alpha change? So yes, I agree 100%. It depends.
Okay.
It depends. No, but it's a good question. But it does. Yeah, it definitely depends on everything else. But I'm imagining everything else the same. How does just the alpha variation change the structure? All right, other questions?
All right, go ahead.
And the non-dimensionalization is not really a problem because it's always easy to measure the size of the tumor.
Oh no, well, yeah. Again, it'll depend. Of course, theoretically we can do it because presumably every tumor has some carrying capacity, right? Tumors grow to be, if a tumor grew exponentially all the time, for instance, you could show that as soon as it was basically diagnosed to be the size of a room or something like that, right? So there's some carrying capacity, right? Again, it'll depend on the tumor, and that'll depend on things, but we have, ideas for different tumors what that size should be. So yeah, but that's an interesting, again, it doesn't matter for the theoretical aspect of it, but it does matter if you're actually thinking about a patient, of course. So we'd have to understand that as well. So yeah, I don't know. It's a good question. we'd have to think about it, or we'd have to, there's some ideas, but it's not like it's just something that's completely fixed across patients or across anything else. So it would vary a little, definitely. But I think it's reasonable to measure. There's some ideas about how to do it in general.
Does the S and R have any identifiable measurable properties?
Yeah, they might in general. Like I said, you could just look at a cell and say how many you can look at a cell and say, how many of those things does it have on its cell surface? So theoretically you could do it, or you could deep sequence, right? They can deep sequence and they can identify genetic or epigenetic markers that might do that. But that's not something that you would do, a general patient would do at every checkup, right? That's the idea. I'm trying to imagine not the best case scenario, yes, you could deep sequence and you could sort of get a good idea of what the tumor looks like at every single time instance. But that's not what people are doing in general. People are going in once a month, getting blood markers, getting some sort of proxy that tells them how big the tumor is, not anything to do with the composition, generally. So you could do it, but it's not what is done on a clinical level.
Other than the problem of measurement, does the model differentiate in vitro and in vivo?
That's a good question. Yeah, it's a toy in the sense that, in vitro, you imagine the carrying capacity is not as big of a deal, right? Because usually in vitro, when people do experiments, They flood them with nutrients. They have so many nutrients that they don't care about how many other people there are. Competition is less of a factor. So in that sense, it's more of an in vivo model because you're actually at least assuming some basic idea about carrying capacity. So some idea about competition. Of course, in reality, it's much, much, much more complicated than what I've written. But I've sort of like the most basic thing that you could write is a logistic growth term that sort of describes some basic competition. But of course, you could always just take k to be infinity, right? Just let k go to infinity, and then you have an exponential model, right? So in some sense, it's a generalization of that.
One more question. In the two equations, modeling S and R,
Yeah.
well, whether it's in the general or
Yeah.
well, probably in more general case, I noticed that there are no R squared term in dsdt and there are no S squared term in dRdt.
Right.
Is there any evidence to show that's the case? I mean, there's no evidence that cells don't collude.
Well, usually people, to die, right? I mean, it's possible,
Not to
right?
die, but,
Well, I mean, that's what it would be, right?
find the other one.
Well,
Okay.
yeah, so it's a good, yeah, that's actually true, right? So, I mean, yeah, so what am I assuming? I'm assuming that, when I write something like this, like there's a certain fraction of the cells that are constantly transitioning back and forth, right? For something like that, right? So, yeah, I mean, so what term did you want the S? You wanted an S squared term that looks like what? Just out of curiosity? I mean, there is an S squared term.
No, there's no S squared term.
Well, there's an S in V though, right?
Yeah,
So
there's an S ultra.
but there's an S squared term as well because V has S.
No, the S squared term is in the first equation, but there's no R squared term in the first equation.
No.
There's no S squared term in the second equation.
Yeah, so what would it be? Well, you're saying there'd be an R squared. I mean, I'd have to try and imagine what that would be. I mean, I like to think of everything in terms of chemical reaction.
If you're talking about general, let's say, predator-prey models,
Right.
wolves, for example,
Uh-huh.
they cooperate.
Oh, right. Yeah, so that's true. Yeah, so that is true. Yeah, so that would be interesting. Yes. So, yeah, there probably is some evidence. I mean, I think there is some evidence that cells have sort of an ideal environment of how much they would like to grow in, right? If they're sort of the rate at which they grow, if it's too low, then they might not grow, but if it's too high, they might not grow. But if there's an intermediate amount of cells, they'll grow very well. So I think there is some evidence to suggest that there is some sort of cooperativity involved in there. Of course, so that would be interesting as well. Obviously, I wanted to consider the simplest nonlinear thing that we could write. But yeah, I mean, I think that is also something to think about as well in terms of division. I think logistic growth, I mean, basically what you're saying is, logistic growth is too simple, right? Basically, there should be some sort of general FSR function. And I agree. There's probably more complicated things that are probably more accurately described. And again, I think that would change things. That would change, again, the geometry of the arc. I think that would change a lot of things. But it would be very interesting. But I haven't considered it yet. All right, other questions? All right, well, thank you.
Thank you.
Thank you.
Yeah, thanks.